Okay, so now it's being recorded, right? All right. So you can expect that in one question that I told you that it will be from 4.12, right? Differentiation. Uh, by section method, you can do that. That was very easy. Let me go to that email. So it says that one bisection method reaches an extrapolation, right? So may need 4.1 for that. So uh, if I ask you, this was 4.2, right? This is 4.2 basically. So in 4.1, basically you approximate f prime at x naught, right? With h and with h by 2. So you will do it 2 times, right? I may give you the answer for that. Maybe I can give you that if I approximate f prime x naught by any formula, and your answer is this for h, and your answer is this for h by 2, right? Now I can ask you that, okay, now calculate n2h, right? Like that. Okay. So this is 4.2 basically, right? So this is a question. If I want to make it short, I may give you the answer to these two formulas like that. I may not ask you to solve it. I may give you the answer directly here. Then you can just use the simple formula, this formula, to get the answer. Okay. And if I ask you the next one, let's say N3H, then it is N2H minus 1 by 15 N2H by 2, sorry, and N2H. Okay. So only difference is, see, it's 1 by 15 here, and it was 1 by 3 at the top. From N1 to N2, it is 1 by 3. And from N2 to N3, it is 1 by 15. So you just have to simply use these three formulas. Okay. So I will give you the trapezoidal Simpson's rule here. One question from trapezoidals and Simpson's rule. I will write it. That so see 4.4. What is the difference? In 4.4 has composite, trapezoidal, and Simpson's rule, right? So basically, in these rules, you are getting right. Uh, Here your n is given. N is given, and usually it is greater than or equal to 2, right? Greater than or equal to 2, and it's given. All right. But and for Simpson's rule, of course, it should be greater than, I think, greater than or equal to 4, because uh, in uh, in trapezoidal rule, your n should be 2, 3, 4, so on. It will be given. And for Simpson's rule, n is usually 4, 6, 8. It is given as an even number. Okay. So if your n is 1 in composite trapezoidal rule, if n is 1, and if Simpson's rule n is 2, right, then they are basically 4.3. Then they are simple trapezoidal and Simpson's rule, right, which are given in section 4.3. So basically, if you know section 4.4, by just putting n is equal to 1 in trapezoidal rule and n is equal to 2 in Simpson rule, it becomes 4.3. So if you understand 4.4, 4.3 is nothing. So I will give you the formulas, but you have to do the partition on your own. I think trapezoidal rule is h by 2, f of x naught, which is a, and then all numbers between them are 2. 2x1, 2x2, 2x3, so on up to 2xn minus 1. And the last one, xn, is again alone, and that is the last number b. Okay. So basically, whenever h is given to you, So whenever h is given, you see, b minus a by n, because n is given to you. So if you divide by that, you get h, right? Then your x naught is of course a, the first one. X1 is you are starting from a and add just one n digit. And then x2 will have a plus 2h, another h. X3 has a n plus 3h. So the last one, xn, which is a plus nh, this becomes b. This automatically becomes b. So you automatically start from a and you end at b. So you will find the function values at all these numbers. Function value at a, function value at x1, function value at x2, function value at b. You will calculate all these and put the values here, function values at all these numbers. So these are very simple, easy rules. There is no problem with that. And this was the trapezoidal rule, composite trapezoidal rule, right? And the composite Simpson's rule is you have a to b, and you always have even number here now. Your n cannot be odd. So I think it is h by 3, and you start with a, and then 2. 2 or 4. I think 2x1, right? 2x1, 4x2. 2x3, 4x. So it's not 2, 2, 2. It's 1 is 2, 1 is 4, 1 is 2, 1 is 4. That's the only difference. So on. And the second last will be 2. And then the last is alone. F of A and B are alone. So 2, 4, 2, 4, 2, 4, 2, 4 like that. So that's the only difference between these two rules.
Victor, Salim.
See, the thing that I was discussing before, that was 4.2, which is here. If you look at this example, you see, you can see with h is equal to 1, h is equal to 0.1, you calculated function by using any formula, and then you made it half. You see, h by 2 will become 0.05. So if you make this half, the new h is 0.05, and you again use the same formula to get these two numbers. So basically, the answer to this is n1h, and the answer to this is n1h by 2. And if you use these two numbers in your formula, they will give you the next approximation in this formula. You see, n1h by 2 plus 1 over 3, n1h by 2, and n1h gives you the next one. And if you use it with 1 by 15, you see, and 2 with 1 by 15 gives you n3. So it's very simple. Right? So I will give you these two approximations, and from here, you can just use these two formulas to get the answer, and 2h and 3h. So it will be a very simple problem. Basically, in the table, these things should be calculated from 4.1. But then after that, from here to here, this is new thing. From here to here, this is new thing. Okay. So I may give you this one. I may give you the first column, and you can complete second and third column like that. So I was talking about composite rules. So let's say let's say here they ask me to use composite trapezoidal rule and also composite Simpson's rule, right? 1, A, 3, right? A. So x 1 to 2 x log of x, n is 4. and n is 4. So if here a is 1, b is 2, right? So h will become b minus a by n. So 2 minus 1 by 4, which is 1 by 4, 0.25. You can just write 1 by 4 as well. You need to write 0.25. So now you see you have to make the values. So your x naught, which was a, right, which is 1, right? And x1 will be 1 plus h, so 1.25, right? X2 will be 1.25 plus h, so 1.5. X3 will be 1.25 plus, so it will be 1.75, and x4, which is 2, and that is b. You see, so x naught is a, x4 is b, xn is always b. So I have these 4 points. So just find the function value. If you want, you can make the tables like xi. You can write again. I put the charger in. So you can make a table 1, 1.25, 1.5, 1.75, and 2, right? So you can write a, x naught, x1, sorry, x1, x2, x3, x4. So now you will calculate the function values at xi. So what is f of 1? My function is x log of x, right? 1 log of 1 is 0. 1.25 log of 1.25. So it is 1.25 into log of 1.25. So that is 0.2789, right? 893. Then 1.5. So you can write 1.5 into log of 1.5. So that is 60819, 6082. Then 1.75. 1.75 log of 1.75, 97933, right? And then at 2. So you got 2 into log of 2. So that is 1.3863. 62963, whatever, right? So I got these two numbers. So this is f of a, this is f of x1, this is f of x2, this is f of x3, this is f of b. All right. Or you can directly write 1 to 2 fx into dx approximately equal to h by 2. H was 0.25 divided by 2, and f of a, which is 1, plus 2f of next point, which is 1.25, plus 2f of 1.5, plus 2f of 1.75, plus f of b, which is 2. Right? So this is trapezoidal rule. Now you have all the values, right? F of 1 was 0, plus 2 into f of 1.25 was 27893, plus f of 1.5 was 6082, 1.75 is 97933, and plus f of 2 is 1.38629. So that's your answer. And if you use Simpson's rule is h by 3, 0.25 by 3, f of a plus 2, 4 or 4, 2. I think I'm missing. Is it 2, 4 or 4, 2? 2, 4. I think this is used twice. 1, 2, 3. 1, 2, 3. Yeah, 2, 4, 2, 4, I think. So you have For even number you have 2, for odd number you have 3, 4. So it means 4, 2, 4, 2, not 2, 4, 2, 4. So that is 4 f of x1. So the first is 1 and 4 1.25 plus 2 1.5 plus 4 f of 1.75 and the last one is the same. So see, the only difference is this 4 and this 4 in above and below formula. Here all are 2, here 4 2 4 2. So I think let me change this one. This is 4. I think what I'm writing. Odd has even has 2 and odd has 3. So this even has 2 and odd has 4. So this is correct. So the last one is 4. 4 2 4 2 4 2 4. Okay, so now you know what are the numbers. 0.25 by 3. So you can replace f of 1, which is 0, plus 4 into 0.27893 plus 2 into 0.6082 plus 4 into 1.75, which is 0.97933, and plus f of 2, which is 380. Right? So that will be your answer. So this is by trapezoidal rule, and this is by Simpson's. Okay? So very easy formulas. Here, one problem is that they sometimes ask you to find the error bound. Error bound is the last term in each of your formula. Your formula is just this. The last term is your error term. So this is the error bound. B minus A by 180, H4 and F4 of mu. Mu is the maximum value of your fourth derivative. So H4 by 180, B minus A, H4 by 180. So error bound is B minus A by 180, H to the 4, and F fourth derivative. Right? Basically, maximum. This is M, where M is the maximum value of the fourth derivative at xi. Okay, where xi is in your interval from A to B. So you have to find the maximum value. If the function is simple, you can find the maximum value. But here your function is not that easy, I think. The first derivative, your fx is x log of x. First derivative will use product rule. 1 log of x plus x 1 over x. So log fx plus. Then the second derivative there, this is easy, 1 over x. Then the third derivative will be minus 1 over x squared. Then the fourth derivative will be plus 2 over x to the power 3. Right? Now, if you want to find the maximum, you see, whenever x is in the denominator, the function always go down like that. Right? 2 over x cubed. If you have any constant divided by x to the power, it's always like that. So it means the first value A will give you the maximum. So your maximum will be the function value at the first point. The last point will be a minimum value. So I can calculate at 2. So it means my M here, which is maximum of F4. What is F4? F4 is 2 over x cubed. And my interval is x belongs to 1 to 2. So it's just the value of this function at 1. This is the maximum value. So M is 2. So now if you just replace M here, you will get the answer. Therefore, my error bound is b minus a, 2 minus 1 over 180. H was 0.25 to the power 4 and m is 2. This is m is 2. So that's your error bound. Very easy. But if, let's say, function derivative of the function is difficult, I may give you the value of m. Okay. Or I can give you the graph. Let's say I can give you the graph of the fourth derivative. I say that, okay, this is your xi and this is the graph. Okay. From A to B, let's say. Right. Now you can easily check that the fourth derivative has the maximum value here. Right. So this is my m, the maximum value at B. So if the graph is given, it's very easy. Graph of f4 x. If that is given, then you can just check what is the highest most value of the function. That is your maximum. Pick that value and put it in the formula. I cannot hear you. Are you talking? Someone said you cannot hear me. I did not hear you, of course, but I don't know whether you were talking. My speaker is on. Um, not have some projected speaker, so I should be able to hear you. Maybe. Can you speak now? I think the projector that is in room C457. I think those speakers are connected with Teams. But anyway, I think now I have selected this correct one. Now I should be able to hear you if you talk.
Doctor,
Yes.
can we solve question 3 in assignment 2? We solve it in a method of forward.
So yeah, that's what I did here. This is assignment 3, right?
Yes.
So here you see this one, right? This
Yes.
one, question 3, assignment 2. This is what I did here.
Yes,
Right?
it's able to, if we solve it in method of forward point, forward method.
If you solve just by forward method, I just need, this is the forward method, right? So
yes,
you just need 2 points now. So x naught plus h. So let's see. Here you have options. You see, the very next point after 1.1, the very next point is 1.2, right? So it means you can use these 2 points with h is equal to 0.1. Another point which is given is 1.3. So it means if I use 1.1 and 1.3, I discard this one, then my h is 0.2. So I can use these 2 points as well to get the answer. Let's say someone says, no, 1.4 is also given. I don't want to use this. I want to use 1.1 and 1.4. So it means my h will become 0.3 for that, right? So I can use 3 different h to get the answer. But he said most accurate. So we know that if h is small, your answer will be more accurate. If you take h big, your answer will not be accurate. So it means I should not be using 1.3. I should not be using 1.4. I should be using 1.2. with the smallest possible h. So my derivative at 1.1 should be equal to f of 1.2 minus f of 1.1 divided by 0.1. This should be my most accurate answer. If you use f of 1.3 minus f of 1.1 and the difference between them is 0.2, that also gives you the same approximation for 1.1. This is also the approximation for 1.1, but this will not be the most accurate. This one will be the most accurate. The accuracy will be better when h is small. Okay? Got the idea?
Mr. Yes, but I mean question 3 when we find N3H, can we use N3H? Can we use the method
Yeah.
of forward?
Now you see, you have to let me show you. You see in question number 3, they said you have to use for 1.0, right? Apply the expression described in example 1 to determine N3H and approximation to f prime 1.0 for the function fx log of x, step size h is equal to 0.4. Now, if you take n1, you need n1 at h and at h by 2. So automatically, first you will go with 1.0 with h.4, right? So it will be 1.4 minus 1.0 divided by 0.4. Agree?
Yes.
Got this formula? So this will be called, whatever answer you get, this is N1H. Okay?
Yes.
The next is again approximate the same thing, but now change h to h by 2. So it means 1.2 minus f of 1.0 divided by h.2. Agree?
Yes, Mr.
So we will call it N1H by 2. That was N1H. This is N1H by 2. Right?
Yes.
So now you can put N1H and N1H by 2 here in the formula. For N3H, you see for N3H, you need N2 at H by 2 as well. So you got from here, you got N2H, right? From N1 H by 2 and N1H, you got N2H. But here you need N2H by 2 as well. For N2H by 2, I need N1H by 4, right? So for N2H by 2, I need N2H by 2. I need N1H by 4 because I have to make it half. When this was H, this become H by 2. If this is H by 2, this become H by 4. Right? So for N1H by 4, I need this approximation again, f prime 1.0 with h by 4. H by 4 will be 1.1 now because h was 0.4. Your h was 0.4. H by 2 becomes 0.2 and h by 4 will become 0.1. So I will do another approximation with h by 4 divided by 0.1. So this will be your N1H by 4. So that you will replace here and here. N1H by 2, you already know. You put it here, right? So now you have N1, N2H as well as N2H by 2. Now they will come here. N2H by 2, N2H by 2, N2H. And that gives you N3H. Okay. So if you look at the table that I showed you, the first column, you need N1H and N1H by 2. This gives you, these two give you N2H. right? But if they ask you for N3H as well, it means for N3H you need N2H by 2, right? But for N2H by 2, that comes from N1H by 2 and N1H by 4. That's why I needed this again, N1H by 4. So 3 elements in first column gives you 2 in the second, and 2 in the second gives you 1 in the third one. Okay, if they only ask you N2H, I will only calculate N1H H by 2 and it will give you N2H. If they ask you N3, I will need these 2 more to get N3H. Okay.
Yes, Mr.
Anything else? So 2. Eilers and Ranchkata. We did Euler method, modified Euler method, Ranchkata method. So I just picked 2 of them from there. And Jacobi's Gauss-Seidel method in 7.3. So see, if formulas will be given to you. So if formulas are given, I don't think it's a big deal. Euler plus Runge-Kutta, one person or 2? One person. So if I show you. So this will be given to you, I think. So we did midpoint method, we did modified Euler method. These are all special cases of Runge-Kutta method, Runge-Kutta method. Runge-Kutta method. But concentrate on this one. All you have to know, this is the initial condition. Y at A will be given alpha. So there, from here you are starting. So this is your starting point W naught. And from W naught, you have to go to the next one, W1. But for W1, W naught, which is given, and you have to calculate all these 4. You are calculating the function value at the initial point, then half step above, not the full step. K2, K3 have half the step, and K4 have the full step, the next one. So what you calculate from here, put it here. What you calculate from here, put it here. Calculate from here, put it here. So this thing is being used in the next one. So this is one iteration. So all these 4 calculation in one iteration. If you have to calculate another one, you go back and redo this one from W1 to W2, W2 to W3. I will ask you a couple of iterations. And Euler method was very simple in 5.2. This was the Euler method. And this will also be written. Where was Euler method? Here is the Euler method. So you see here, everything is there. You see, if you look at the Runge-Kutta method, you only have K1. See, this was K1. If you see the Runge-Kutta method, your K1 is H of FTIWI, right? Then we use this K1 somewhere to get K2, to get K3 and so on. But here you just have WI plus H, which was just K1. In your Runge-Kutta method, your WI plus 1 was WI plus 1 by 6 and K1, K2, K3, K4. So it's a simple one. You are just.
Doctor, please, can we give him an example?
No. Did many examples in the class, right? You guys keep sleeping. Where is the example? Where is the example in front of you? Where is the exercise? Which question I gave in the, I think this question I gave in the assignment, right? Was this the question? But anyway, we can pick that. Is that use Euler method to approximate? This, right? This is section 5.2. This is section. I may give you same question and I say use both the methods, right? Use Euler method to find the solution, then use Runge-Kutta method to find the solution. Compare your answer. Which one is better, right? So in the same question, I may give you both. So here you see, this is my f of ty, right? The right hand side is f of ty. This is my a0 and b1, right? This is my alpha. The right hand side initial value prop, right? And this is my h. Everything is given. So what we can do, either we can just make that we are starting from, so first of all, what will be your t? Your t0 is a, right? Which is 0, right? Then t1 is a plus h, which is 0 plus 0.5. So 0.5. And t2 is a plus 2h, which is 0.5 plus 0.5, which is 1. So that is your B. So I only have 3 points there, 2 steps only, from 0 to 0.5 to 1. So I have just 2 iterations of the Euler method here, right? Just 2 iterations of the Euler method automatically. I will not write the 2 iterations. How you will get? You will get the iteration from the interval that is given to you. If I change this interval from 0 to 2, right, I will have 2 more points, from 1 to 1.5 and from 1.5 to 2. So you will have 2 more iterations. So there will be 4 iterations. Okay. So based on the interval, you have to decide how many iterations you have. Now, W naught is alpha, which is 0, right? This is the starting point. Now, calculate f at t0, w0. F of t0 is 0, f of w0 is 0, and the function will become 0, 0, 0. It will remain 0. So therefore, my w1 will be w0 plus hf of t0, w0. So w0 was 0 plus h is 0.5, and this remains 0. So your answer is again 0, right? So now w1 is this. Now find the function value at t1 w1. The next point. So t1 is 0.5, right? This is t0, this is t1, this is t2. So f of t1 is 0.5. W1 is still 0, but now my t is 0.5. So this is 0.5 e to the power 3t, which is e to the power 3 into 0.5, and minus 2 y is 0 here, right? So you got 0.5 e to the power 1.5. So you can find the answer here. 0.5 into e to the power 1.5. So that is your 2.2408. Okay. Now, Now go to the third one, W2. So therefore, W2 is W1 plus H F of T1 W1. So W1 was 0, right? W1 was again 0. So this is 0. H is 0.5 and T1 W1, F of T1 W1 I just calculated. So 0.2, sorry, 2.24. 2.2408, right? So now multiply this by 0.5, multiplied by 0.5, 1.1204. So that's your answer. That's it, right? This is the value at. So see, W1 is Y at 0, right? W1 is approximation at T1. It's approximated by W1, which is also 0. And this is Y2. Y at 1 is approximated by W2, which is 0. So this gives you the approximation of Y at the last point, which is 1. Okay. So these are the three approximation, only 2 iterations. If you use Runge-Kutta method for that, okay. If I use for the same question, if I use Runge-Kutta method, then I will start with the same W naught is equal to alpha, which is 0. But then I will calculate K1. K1 is H of FT0 W0. Okay, which I calculated above. H is 0.25, right? F of T0 is 0, W0 is 0, and that gives me 0. Sorry, H is 0.5. Right? So now K2. K2 is H F of T naught plus half H by 2 and W naught plus K1 by 2. Okay, so I know that H is 0.5, F of T naught plus half. T naught is 0 plus H by 2 is 0.25 and W naught is 0 plus K1 is also 0. This will go here. This is K1, which will come here. So this remains 0. And now it is 0.5. F of 0.25 is 0. T e to the power 3t minus 2y. Right? Your function was, I can write it again here. F of ty was t e to the power 3t minus 2y. T e to the power, yes, right? So you see, if I calculate f t 0.25 and y0, so you will get that. So if I calculate this one, you will get 0.25 into e to the power 0.75. So that is 59 and multiplied by 0.5. That is 0.264625. Okay. Now K3. K3 is again H F of T naught plus H by 2. It is the same. This does not change. Second will change W naught plus K2 by 2 now. Now this is K2. So this point will come here. Okay. So that is H, which is 0.5. F of this is the same as the old one, right? 0.25. And W naught was 0 plus K2 by 2. So K2 by 2 is 0.2646 divided by 2 is 1.31. 1.3231. Okay, so this is what you have. Now, if you calculate 0.5 is outside, my function is 0.25 e to the power 3 into 0.25 t e3t minus 2 into y. Y is 1.32, 0.132. This is 0.132. Okay, so calculate this one. This is your K2. Whatever answer you get, you put it in K4. K4 has H of FT1. Okay, you start from T0. You see, in Ranchkata method, you have T0 and T1. But for K2, K3, for K0, for K0, you use T1. For K4, you use T. But for K2, K3, you pick the middle value here, which is T naught plus H by 2. You can see here, T naught plus H by 2, T naught plus H. So for K2 and K3, you are using T naught plus H by 2. Okay. So for K4, you got the next point T1. And here it is W naught plus K3 by K3 only. We don't divide by 2 here. K3. Here you see K4 has HT1 and W1 plus K3. I'm not dividing by 2. Here you see, these both are half. H by 2, K by 2. H by 2, K by 2. Here there is no H by 2, no H by 2, no H by 2, no H by 2. So that's how you can remember. But anyway, this will be written in your question, so don't worry. So now H is 0.5. F of T1. T1 is the next point, which is 0.5, not 0.25, right? And W naught was 0 plus K3. K3 is this, just coming from here. So let me calculate if you want. 0.25 into E power 0.75 and minus 2 into 0.1323.25. So if I do that, multiplied by 0.5, it's 0.1323.125. The same as this one. Anyway. So now this will come here, 0.1323.125. And this will be 0.5 into function is 0.5 e to the power 3 into 0.5 and minus 2 into y, 1323.125. Right? So let's do this one now. 0.5 into e to the power 1.5 minus 2 into 0.1323125 is what you got, and multiplied by 0.5 outside. So that is 0.988109109711, right? So you got now K1, K2, K3, K4. So therefore, my W1 is W naught plus 1 by 6 K1 plus K2 plus K3 plus K4. I think K2, K3 comes with 2. 2K2, 2K3. 2K1, 2K3. So now you have all the values. W naught is 0 plus 1 by 6. K1 was 0. K1 is 0 plus 2 into K2 was 0.264625 plus 2 into K3 0.1323125 plus K4 0.98819. Okay, so this is your next step. So whatever you get, that's your W1. So in Ranchkata method, even one step will take some time. And if you want to complete this question, of course, there will be second step from W1. You will again calculate K1. K1 is now H1 because it's step 2 now. Now I is 1. Oh, sorry, I is, yeah. First it was I was 0. In step 1, your I was 0. So now K1 is f of T1W, right? So H is 0.5, T1 is 0.5, and W1 comes from here. This is your W1, right? Then K2, which is H of f of T1 plus half H, and W1 plus half K1. Now K1 comes from here. Then K2, 3 is equal to H f of again T1 plus H by 2, and W1 plus half K2. Now this is your K2. Whatever that is, so this will come here. And K4 will be H of F T2. Last one, K1 is T1, K4 is T2. Middle two are T1 plus H by 2, T1 plus H, and W1 plus K3. So whatever K3 you get, put it here, get K4. So now therefore the next is W2. W2 is W1 plus 1 by 6, K1 plus 2K2 plus 2K3 plus K4. But these are the new Ks. These are these 4 Ks, not the old one. Old Ks are already used. In first step, you have already used these old Ks. Now in the second step, there are new K1, K2, K3, K4, and they will come here. So this will complete the proof because I only have to go up to W2. This gives me the approximation at W. This gives me the approximation at 0.5. Okay. So these are simply your Euler's method and Runge-Kutta method of order 4. So the last one was Jacobi's and Gauss serial iterations. Right? They are both in 7.3. Only thing is, when the system is given, you from the first equation, you write x1 and send everything on the other side. From the second equation, write x2 and send every other thing on the right, x3 and so on, right? And whatever x's are used here, let's say x2, x3, whatever they are using, use 0 first initial guess, basically, okay? And this gives you the first guess, first iteration. So if you put 0, 0 in the right hand side, you get a 1, 1 on the left. Then if you put 1, 1 on the right, you will get 2, 2 on the left, right? That is your Jacobi's. In Gauss-Seidel iteration, they say if you write x1 on the left and send everything to the right, x2, x3, whatever on the right, keep x2 here, send every x1, x3 on the right, keep x3 on the left, send everything on the right, x1, x2, right? Now, if you use the initial guess 0, 0, you get x1. But because you already have a new x1, so why use the old x1 0 here? Why not use the new x1? Here you see, I use the old x1. I did not use the new one. But x3 is already old, so it will remain like that. Now it gives you x2 at 1. Now you see x1, you have the new one, and x2 also you have the new one. So if you use the new x1, x2 here, it gives you x3 at 1. So that's the difference between Gauss-Seidel and Jacobi's iteration. Jacobi's says that no matter what, on the right hand side in all the equation, use the previous guess. Okay, but Gauss-Seidel suggested that whatever new you have gotten, while you still using the previous x10 when you have a new x11. So for next equation, you can use the previous updated value of x1, x2, x3, x4. This is the only difference between these two. Very simple methods. I think I shared this on the Moodle, right? So I gave some hint here. So you can see that here. I wrote x1 on the left. You see x1 on the left, right? And every other thing on the right. 1 plus x2 plus minus x3 and divided by 3. Of course, I will divide by 3, right? And then I will keep x2 from here. x1, x3 will go on the right side and divided by 6. Then I will keep x3 here. x1, x2 will go on the right side and I will divide by 7. So you got this system. Now if you put 0 on the right, you see 0, 0, 0, 0, 0, 0 everywhere. Then it will give you 1, 1, 1. That is the Jacobi's iteration. Okay. But if you use Gauss-Seidel, then you will not use 0 here. You will use 1 here because you got x1. So why not use 1 here? Then you got x2 1. So why not use x2 1 here, 1 here? So see below the diagonal, you will get the new one. Above the diagonal, you still have old one. You see, above the diagonal, you still have 0, 0, 0. But below the diagonal, you have 1, 1, 1. That's the only difference between Jacobi's and Gauss-Seidel iteration. So this example, you can see they did Gauss-Seidel iteration here and Jacobi's iteration here. Okay. So this example will give you a good idea. I think that's enough now, right? So I will save it and upload. I can write here. You can so this is the question I was talking about. So you can pick, yeah, they are saying that repeat exercises with Gauss-Seidel. So you can pick any one question and try Jacobi's and Gauss-Seidel. The way of writing for both is the same, right? You will pick x1 from here, x2 from here, x3 from here. But remember, if you look at the coefficient of x1, your a11 should be greater than or equal to a12 plus a13. So if you combine these two, and these are not without signs, basically the absolute values without signs. So it's minus, but the number is 1. So if you pick 1 from here, 1 from here, so 1 plus 1 is 2 and 3 is greater than 1 plus 1, you see. And here 6 is greater than 3 plus 2, you see. 6 is greater than 3 plus 2. Here 7 is greater than 3 plus 3. Okay, so these are called diagonally dominant. So your systems will be diagonally dominant. Then you can pick that. Okay, so see 10 is greater than 1 plus 0. 10 is greater than 1 plus 2 and 10 is greater than 1 plus 2, right? Diagonally dominant, all of them. So anyway, just pick x1 from the first one, right? X2 from the second one, x3 from the third one. And for first iteration, write 1, 1, 1 here and 0, 0, 0 on the right side. When you are done with first iteration, then write the second one, x1, 2, x2, 2, x3, 2. And 1, 1, 1 will be here. x2, 1, x3, 1, x1, 1, x3, 1, like that, okay? And x1, 1, x2, 1. 1 comes here, 2 goes there. But if you are doing Gauss-Seidel, then this is 1, this is 2, this is 2, this is 2. Right? Below the diagonal, it will become 2. That's the only difference. So you can, for practice, just pick any other one. If you can pick this one if you want. Okay? Here also it's diagonally dominant. 4 is greater than 1 plus 1. 3 is greater than 1 plus 1. 5 is greater than 2 plus 2. So they are diagonally dominant. You can easily find x1, x2, x3. Bring every other thing on the right hand side and make the iteration scheme. All right, I think we have covered almost everything. So you can, for practice, you can do 1A or 2A with both the methods. Right? Jacobi's and Gaussian. So that will be enough practice. All right, guys. If you have any questions, you can ask. Otherwise, I can stop, save the video, and upload on Moodle.